This project focuses on Ethernet for cyber-physical systems, abbreviated as CPS. It is funded by the NSF and the principal investigator is Professor Liang Cheng. CPS are engineered systems that are built from, and depend upon, the seamless integration of computation and physical components. Ethernet is used to connect different components of CPS, and it is widely applied to industrial control systems, avionics systems, and vehicular networks. With the development of Industry 4.0 and 5G, more and more sensors and actuators are added to those networks. The delay will increase when there are more flows in the network. However, there are time-critical flows existing in networks which require a guaranteed maximum end-to-end delay. That is the reason why we want to implement the deterministic performance analysis of cyber-physical systems with random processes. The aim of our project is to establish a systematic way to design, characterize, and refine the network infrastructure in CPS to meet the requirements of time-critical flows. Moreover, we want to develop both software and hardware for the outer research groups. An additional aim of the project is to develop a method to analyze non-feed-forward networks, in contrast to state-of-the-art methods that target feed-forward networks. Non-feed-forward networks are networks that have cycles. We use network calculus as the theoretical framework for this project because it is designed to provide deterministic performance guarantees in computer networks. First, we must introduce network calculus. To use network calculus, we should characterize the flows and switches with arrival curves and service curves, respectively. An arrival curve is the upper bound of the cumulative curve of the packets arriving to a node. The service curve is the minimum performance which is guaranteed by the switch. In Figure 1, S is the network node which is also the network switch. A network switch is networking hardware that connects devices on a computer network. Alpha T and alpha prime T are the arrival curves of the input traffic and the output traffic of the switch S, respectively. Beta T is the service curve of S. Alpha T and beta T are curves we want to create. These are the curves used for network calculus latency analysis. The red line in Figure 2 is the arrival curve and the blue line Indiana the figure is the service curve. The maximum end-to-end delay is the maximum horizontal gap between two lines which is H alpha beta. Next, we will introduce the topology of the test bed. In this experiment, we use a 4-node tandem network topology which is shown in the figure. The network topology can be modified easily by changing the connection between switches and the number of switches. In the photo of the test bed, cables are connected if they have the same color of label. The Ethernet port with the orange label is connected to the receiver and the black cable with the blue label is connected to the sender 1. Our test bed provides a way to create arrival curves for data flows and service curves of the switches. Then, we can feed these curves into a network calculus analysis to get the analytical maximum end-to-end delay bound. The analytical delay results are compared against the empirical test bed delay results. The analytical results should upper bound the empirical results. Last, we can calculate the maximum bound of end-to-end delay based on the arrival and service curves modeled by the test bed.
We use a network calculus toolbox called DiscoDNC to do the calculation. It shows the resulting upper bound, which is approximately 0.37 seconds. The empirical measurement is 0.174 seconds, which is well below the upper bound. This comparison shows a limitation of the network calculus, which is the tightness of the bound. Since network calculus takes the upper bound of input traffic and the lower bound of the guaranteed service, the discrepancy between the analytical bound and the measurement result might be large.